like about 4.5 hours or 4 hours even. Yeah. Anyway. So let's. So yeah. First of all, we're going to talk about the schedule a little bit. So on Monday, I talked about this schedule, but we're going to modify it a bit. So I'm going to swap these two basically. So, but before that, we're going to talk about some graph problems that we didn't have time yesterday. I mentioned that I still have some problems left that we ran out of time. So we're going to talk about that first. I think there are 3 or 4 problems. And then after that, we're going to date. So we have 3 contacts already. We're going to talk about the contacts and the problems there. We discuss some of the maybe just the 3 or 4 hard ones for each day. And then of course if you have questions missed. And then if you don't have time to finish all of them today, we are going to bring it forward tomorrow. The special topic should be not that long, should be short. And of course tomorrow we'll also talk about the context from today as well. Unfortunately we won't have time to discuss the task for tomorrow's context, but yeah, you can discuss among yourself, or if you have questions, let me know after the context. I'll still be still around. But we won't have class, I think so. But yeah, you can ask me questions. Yeah. But tomorrow I'm going to make it because it's the last day, the test day. Going to make it a bit different than usual. The topics and the content is going to be more on the fun side, but still you will still learn something. But it's going to be special. You'll see tomorrow what I mean, right? Okay. So yeah, that's the idea. That's the schedule, right? So as I mentioned, we're going to talk about some graph problems again. So yesterday we talked about this. No, I mean on Wednesday, and we talked about this as well. And so I think this is where we left off yesterday, 2 days ago. Sorry. We're going to continue talk about some graph problems. Okay, so this stuff is from 13 years ago. Google could the problem is called stock chart. So let's say you are given n stock prices, and for each stock price, it's a line segment connecting. So for each of the stock, so n stocks, for each of the stocks, you're given P0, P1, P2, blah blah blah, and basically it means that the stock price is from 0 P0, 1 P1, and so on, right? And then we want to group these stocks into overlay charts. So you know where in one chart you can have the price of several stocks. So you can make something like this, right? But if you want to group 2 stock prices together in one chart, the line must not overlap, right? Because otherwise it's confusing, right? So we want to know how many minimum number of charts we have to make to group all these stocks together. Yeah? Okay. How do you create the graph as a graph?
Well, because of the both graph that can intersect, one of them is always over the other.
Okay.
And that is a partial order.
Okay.
You can create that and divide that with pi.
Okay. So you're saying if stock prices U is always on top of P, you create an X like that?
Yes.
Yeah, and then if they overlap, you don't create an X. Okay, and then so it's actually correct. The idea is that we can create a graph, and then becomes partially ordered set, and then we want to find, in this case, it's the number of parts or the number of maximum independence that is the same, right? Yesterday we talked about the word theorem, and then we want to find that, and the way we do that is, remember how we create a bar type graph. If there is an S like this, we add U on the left to P on the right, and then it's the n minus the maximum number of matches. Right? Okay? So, you can solve this question. Okay, next question is from Professor Sean, educational. So let's say that there is a set of n positive integers less than b. So like the integers in the set. So there is a set of basically it's a subset of this, right? F is a subset of this containing n elements, right? Okay. And then it's also guaranteed that from all 0 to 4, the number of integers x where x mod not x mod k, sorry, x mod 5 equals k. Okay, this is critical. I need to fix now because this changes the problem. Okay, x mod 5 equals k is the same. So x can be like 0, 1, 8, 12, maybe 4, right? So there is exactly one element that gives you that is mod 5 equals 0, mod 5 equals 1, mod 5 equals 2, right? Okay? Yeah, so this is possible, but this is not possible, right? So yeah, the set X is guaranteed to satisfy that property. This also means that X the number n is a multiple of 5. Right, okay. Now you are given few things. Each in the form of there are UI integers in the set, there is not more than VI. So yeah. For example, this one of the possible hints can be like there is 4 integers, not more than 10, something like that. Right? Which is this and this. So yeah, you are given the hints. Of course, you are given n, you are given b, you are given the hints. You want to determine whether such set exists. This and b. And n is a multiple of 5. If n is not multiple of 5, then it definitely cannot happen. Right.
UI and VI big?
It's bounded by n. Sorry, bounded by b. EI is bounded by b, UI is bounded by n. Yeah. EI is bounded by b. There are UI integers in the set of n. I mean, if UI is greater than n, it's obviously cannot happen, right? Because there are in the set there's only n integers.
Can you repeat the numbers?
No. The set is a set. Distinct element. Yes. So yeah, just for example, if the input is like N5, B12, and then the hint is U1 is 4 and P1 is 10, then the answer is yes, because this is one of the possible examples, right? Yeah.
Can be with flow.
Sorry?
Can be with flow.
With flow, yeah. Maybe yeah.
So if I understood correctly, like so the key carries will plot like segments of
Yes.
option number, and you can do like terms to match. No flow, like can you do with flow?
How?
Like each number can only receive one flow, right?
Okay.
And like for each segment, we have a number of guys that we receive.
So let's say this is the segment. This is the segment. And then what do you do with this? You connect to source, let's say.
To the numbers that they refer to. Like, let's say that's the segment from 1 to k equals x. Okay?
Okay.
So like I have x flow to the nodes from between 1 to x. I can distribute x flow.
So let's say there are 4 intervals. Okay. This is 1, this is B, right? And then you create 4 nodes, yeah? And then do you connect this to source or sink or?
Actually, I think you can like create 5 nodes for each module, and with math you can calculate how many numbers there are in each segment that connect to.
So you create 5 times 4?
No, it's
Just 5.
5 plus 2.
Okay, okay. So let's say this is 5. So this is k from 0 to 5, right? And then from 0 to 4. And then for each of these intervals you create a node as well. And then how do you connect them?
Like let's say that from a segment I calculate how many numbers there are modules.
Yeah, okay. So let's say this is basically how many, like, let's say this is 0, then how many integers in this range mod 5 equals 0, right?
Yeah.
Okay, and then, so that's the capacity of this x, but what is the capacity of this and this?
So basically this is the number of the next one is the number of values that are present in the segment that
Okay.
we can extract.
Uh-huh.
And to the right, I think it is n divided by 5.
Yeah, okay, yeah, so, yeah, correct, okay, yeah, yeah, basically, yeah, this one is how many failures should be here, which is like pi minus 1, something like that, if you sort the u, sorry, the other way around, ui minus ui minus 1, if you sort the v, right, so yeah, that tells you how many integers should be this range, and then here is, how many integers between 1 and b is, if you mod 5, you get this. So it's not necessarily n over 5 if the b's have some excess. So some of this might be n over 5 plus 1, n over 5 plus 1, but this is n over 5, b over 5. Huh?
No, you have n elements in total.
Oh yeah, correct. Sorry. Yeah. This is n over 5, n over 5, n over 5. Correct, yeah. Okay, yeah, and then you just run max flow, and then you make sure that all of these things, the answer is n basically, right? All of these things are full, yeah. Yep. Okay, yeah, correct. Yeah, there's another solution that you can avoid max flow at all using Hall's theorem, because this is bounded by 5. You can do 2 to the power of 5, and then for each of these, you basically make sure that the sum of this, so basically, let's say this is connected like this. Yeah, let's say you try this subset. You have to make sure that so Hall's theorem kind of work for weighted as well, like weighted flow, weighted if there is a capacity like greater than 1. Like yesterday I showed you for matching, which means that all of these capacity are 1, but it also works if all of this is weighted, which basically means that if you try this subset of nodes, you find out something like this. So let's say this is A, this is B, this is C, D, E, F. Then you take something like the minimum of A, C plus D plus the minimum of B, E, and F. Which basically means that this part is how many flows can go through here. It is the bottleneck either A or C plus D, right? And then this part is minimum of B, E plus F. And then, yeah, if this is more than 2n over 5, then this subset is okay. But if there is at least one subset that this is not satisfied, then it's actually impossible to get flow equals n. So yeah, you can use Hall's theorem as well, and you don't need to put max flow or Yeah, max flow. You have to use max flow on this because it's bigger. Or maybe then algorithm. I don't know. Yeah. Alright. Yeah, because this is small, you can do it. But it's just another solution. Okay. Yeah, so that's good. This is correct. Okay, next problem is from this last year's code jam, actually around 3 master maze. So yeah. So let's say you are given a directed graph with 10 vertices, each vertex has 2 outgoing edges, color the graph with 13 colors such that the outgoing edges cannot be assaulted, yeah? Must point to a different node. Such that for all paths U, V, W, all of them have different colors.
Can you do one step of transition and after that the normal coloring?
Okay. So what do you mean one step?
Because I mean, you have U to V and V to W, and you add an edge from U to W, and that will be advanced whole original edge because the ongoing degree is at most 2. So you have each node with all degree at most 6, and you can color it either with 7 colors and this no?
But it can have incoming as well, no?
But you can order in reverse topological and coloring, and when you will color a node, you will reach at most 6 other
There
nodes.
might be cycles.
No, I understand. Okay, I understand.
Isn't it true that there's always a node that has? Oh, okay, forget it.
Yeah.
You can just throw what you said before you do SCP, and then for each cycle you read every color, and then you do the reverse topological cycle.
How do you color in one ICC?
You can just read every color.
And then in one ICC you color with the same color?
Sure.
No, you cannot do that, right? Like, because in one ICC there might be several nodes, and if in this one ICC you color with all the same nodes, then you will violate this option. Yeah.
What is that? Like, basically, you're taking the square of the graph.
What? The square of the graph, yeah, okay.
So you know that the outer green will be at most 6, right?
Okay. Yeah.
And in the green, it must be like at most 6.
Oh.
Also.
The in degree of this node is here.